So today is the third class on group theory. So lecture 3. And when more people come in, I'm going to talk about the time, because it turns out that the poll has shown that we don't have a common time within the range that I indicated. So, but let's just wait a little bit for more people to come in before we discuss that, okay? So while we wait, are there any questions for previous time?
Since the class activities are already due, could we talk about how that proof for the Lagrange's theorem went?
Yeah, we can, but I think I would like to give it a little bit more time, because some people haven't actually submitted it yet.
Sure.
I haven't attempted it yet. I would like to try it.
So
myself
yeah,
first.
let's give it a little bit more time, okay?
All right, no problem.
Yeah.
Sir, I have a question. Any action or applied on a set, is it a group? I mean, group without action is just a set, right?
It's a very specific action. It's the action that we indicated. So not any action would be. So for example, the set of, you can have actions on a set which make it, say, a field. You can have actions on a set which can make it a semi-group. You can have actions on a set that can make it like a, I don't know, a ring or something like that, right? So, so the group is a set with the action that satisfies those axioms, that it is closed under that operation called multiplication. Operation is associative. For each element, there's a unique inverse, and there is an identity element such that the multiplication with the identity element always yields the element, and the identity is its own inverse. So those are the axioms that make that set a group. So the operation can be many things, but the operation that satisfies those conditions is what makes it a group.
Okay, sir, got it.
Okay, any other questions?
Sir, what are the consequences of significance of having abelian groups versus non-abelian groups? Firstly,
it's just, the group definition does not require it to be abelian, right? And there are far-reaching consequences, like in terms of applicability. I mean, there are mathematical consequences, but there are also consequences in terms of applications. And one of the most important application is that, there are many representations of groups by matrices is common. It's not just common, it's overwhelmingly common. And if you think of matrices, suppose you have a group, say G1, G2 gives you G3, and a matrix representation would be some matrix M, which is a function of G1 times some matrix M. So this is a map, right? So this is one matrix. You can call it M1, but I'm just calling it MG1, MG2. And this is matrix multiplication, okay? So this is and then you have M of G3. We could have written this as, say, some matrix M1 times M2 is M3. So if this is valid for all the elements of the group, then we say that this is a representation, that M is a map from the group to some subgroup within, say, I don't know, GL and R or C, but this map is a representation. M is a representation of the group G. Now, if the group was abelian, that means that G1 times G2 was equals to G2 times G3, then the subgroup of GL and C would be a very small, it would be a very small subset. We know that matrix multiplication. So matrix multiplication is non-commutative, right? So in general, two matrices, if you multiply them, M1, M2, that's not equals to M2, M1. So a group being non-abelian means that it has a very good possibility. In fact, I think it's always the case that it can be represented by matrices. So that's one thing. The other thing is that many symmetries that we deal with in everyday life and physics are non-abelian. So for example, if I do rotation in 3 dimensions, so if you take a book, so a book is a nice object because, it's not symmetric, and you put it in some, space, say, so that's a z-axis, that's a y-axis, x-axis. And if you do a rotation around, say, z, and then you do a rotation around y, that is not going to give you the same as rotating it around y and then rotating it around z. Okay, so I'd like you to try this at home. So that means that rotation in 3 dimensions is not a commutative operation. So if you're going to represent rotation by a, by groups, then you might, you have to make sure that it's a non-abelian group, right? Okay, any more questions? Well, did that satisfy your curiosity? I don't know. I mean, it's a very broad question.
Yes, sir, thank you. It was
there could have been many, many answers.
Yes, sir, thank you.
Okay, somebody asked something in the chat. Let me see if I can reach over. Oh yeah, okay. So it's the same. Any other questions?